Welcome back to Logic, Language and Information 2, and to this, the first in a series of lessons on mathematics and logic, particularly the importance of quantifiers for mathematics. There are multiple layers or levels of relations between mathematics and logic. At the foundational level, mathematics is grounded in logic. Much of contemporary mathematics can be formalised in set theory, and in turn, set theory can be formalised in first-order logic, which is predicate logic with identity and functions. In addition, logic is also positioned as a branch of mathematics, a subfield within the broader discipline. Admittedly, it is one of the most abstract branches of mathematics. This abstractness, together with the foundational role of logic, may at least partially explain why logicians tend to be the eccentrics within mathematics departments. At a practical level, doing and using mathematics requires logic. Each step taken within a mathematical proof must be a valid inference that could, in principle, be formalised within logic. Furthermore, the precision of logical constructs and tools are valuable in clarifying and understanding complex mathematical concepts. It is this aspect of the relationship between mathematics and logic that we will be exploring in this series of lessons. Consider the following sequence of numbers that is decreasing in order. It starts 2, 1 1/2, 1 1/4, 1 1/8, 1 1/16, 1 1/32, and so on. Intuitively, we have a clear sense that this sequence is tending to the value 1, getting closer and closer, but never quite getting there, even as the count index n goes to infinity. We say the limit of the sequence is 1. The notion of the limit of a sequence seems intuitive enough, but it is surprisingly complex. Drawn here on the number line, we see the terms of our example sequence as red dots getting closer and closer to 1. At the scale we start with, the red dots get blurry after about term A4. The meaning of the phrase getting closer and closer is that we can zoom in or magnify close to the limit and there see the same behaviour of sequence terms AN, the red dots in the graph, approaching 1 from above. Again, the red dots quickly get blurry, so we might do another zoom in or magnify close to the limit and still see the same behaviour of red dots approaching 1 from above. The red dots quickly get blurry, so we can again zoom in or magnify close to the limit and still see the same behaviour of red dots approaching 1 from above. Once more, the red dots quickly get blurry, so we can again zoom in or magnify close to the limit, and still more of the same behaviour of red dots approaching 1 from above. The notion of a limit of a sequence is that we could zoom in or magnify infinitely many times, and each time we would still see the same behaviour of sequence terms getting closer and closer to the limit number. Consider another quite different sequence of numbers. It goes 1 minus 1, 1 minus 1, 1 minus 1, and so on. A sequence that has a limit is said to converge, and otherwise the sequence is said to diverge. This series of lessons will work up to the point of making precise the notion of a sequence of numbers having a limit, and formalise this in the predicate logic taught in the core part of this course. Crucially, we will need the logical quantifiers for all and there exists to unpack the complex content of the concepts of convergence and divergence. Historically, there were a number of very important concepts that caused confusion amongst mathematicians until they were given precise logical definitions in the 19th century. These include fundamental notions in calculus and analysis, the continuity of functions, the derivative of a function, and an infinite sum having a well-defined value. In fact, each of these concepts depend on or make essential use of the notion of a sequence of numbers converging to a limit. Now, do not be worried that you will need calculus to follow these lessons. There will be no further mention of continuity or derivatives. I promise all you need is basic high school level mathematics, which I will review as needed, together with the predicate logic with identity as covered in the core part of this course. Take a look at the YouTube video with the link on the screen for the astounding and indeed invalid proof that the infinite sum 1 plus 2 plus 3 plus 4 plus 5 and continuing going through all the whole numbers adds up to the finite value of negative 1 over 12. By the end of this series of lessons, you'll be able to explain, using logic alone, what is wrong with the supposed proof. Convergence of sequences of numbers has a very long history. A famous early example is Archimedes' approximation for the number pi, dating back to more than 200 years before the Common Era. Remember from geometry that pi is equal to the circumference or the length of the perimeter of a circle of diameter 1. Geometrically, we can see that by taking polygons with more and more sides, it will get closer and closer to the circle. The image shows the start of the lower approximation sequence coming from inscribed polygons with 4, 8 and 16 sides. The upper approximation sequence comes from the perimeter of circumscribed polygons with the polygon on the outside of the circle. Archimedes, or perhaps his assistant, calculated by hand up to 96-sided polygons to get the lower approximation of 3 and 10 over 71 and the upper approximation of 3 and 1 over 7. Now, pi to 6 decimal places is 3.141592. So Archimedes got within an accuracy of 1 over 100. And he gave a clear description of how to continue on the approximation sequence indefinitely by taking polygons with more and more sides to get more and more accurate approximations. Now, pi itself has an even older history. As early as 2000 BC, people in ancient Babylon, Egypt, China and Israel independently discovered the fact that the circumference of a circle is directly proportional to the diameter. The earliest known sequence is that approximating the square root of 2, produced by Babylonian mathematicians using geometric reasoning in the period of 1800 to 1600 before the Common Era. The Babylonian clay tablet with the code name YBC7289 shows a sequence of calculations leading to an estimate of the square root of 2 as the fraction 30,547 over 21,600, which is accurate to 6 decimal places. The funny fractions come from working sexagesimally, which means in base 60. Later Babylonian artifacts show that a knowledge of a recursive formula for calculating better and better approximations. The new approximation a sub n plus 1 is calculated from the current approximation a sub n using the formula a sub n plus 1 equals a sub n over 2 plus 1 over a sub n. Coming forward to the 17th century, where we saw the development of calculus by Isaac Newton and Gottfried Leibniz. Newton in particular was very fond of using infinite sums, but without a rigorous basis, and sometimes in error. Newton's version of the calculus made extensive use of the notion of an infinitesimal quantity that was smaller than any normal number but different from 0. In the early 19th century, the German mathematician Carl Friedrich Gauss started a new push to clarify the notion of convergence for sequences and infinite sums, but further work was needed. Soon after, the Czech, or then Bohemian mathematician Bernhard Bolzano in 1817 took up Gauss's call and gave the first formulation of the modern version of sequence convergence, with his natural language formulation including the for all there exists for all pattern of quantification that we will get to a few lessons ahead. This was 60 years before Frege's development of predicate calculus, so the meaning and logic of the quantifiers had yet to be clarified. Bolzano's work was not well known, and in the first half of the 19th century, it was soon eclipsed in notoriety by the work of French mathematician Cauchy. Cauchy's better-known formulation of sequence convergence, and also continuity of functions, was framed in terms of these infinitesimal quantities, as part of a research project to give Newton's infinitesimal calculus a rigorous basis. Nevertheless, Cauchy's version of sequence conversion was a step down from that of Bolzano and led to a famous mistake by Cauchy confusing continuity and uniform continuity of functions. Around 1860, the German mathematician Karl Weierstrass gave a series of lectures in Berlin which became the gold standard for the rigorous development of sequence convergence, continuity of functions, and other key concepts. Weierstrass was particularly indebted to Bolzano in his formulation of sequence convergence. Less than 20 years later, and heavily influenced by the work of Bolzano and Weierstrass in mathematical analysis, Gottlob Frege presented predicate calculus, published as Begriffsschrift or concept notation, subtitled A Formula Language of Pure Thought Modelled upon that of Arithmetic. An intellectual struggle in mathematics to make precise, complex mathematical concepts was a major impetus to the development of predicate calculus. And then in turn, the development of predicate calculus made possible the even more rigorous formulation of those concepts, as we shall see in this series of lessons for the concept of sequence convergence. The notion of sequence convergence is important. It is used widely within many areas of pure and applied mathematics, as well as in applications within science, engineering, economics, medicine, and other disciplines. When a sequence of numbers represents the dynamic state of a process changing over time, convergence properties of the sequence correspond to what's called the asymptotic behaviour of the process in the long run, so to speak, as time goes to infinity. Convergence of sequences is also the mathematical foundation for many approximation methods used in science and engineering, as well as for the digitised representation of real numbers in computers. In the remainder of these lessons, we will progress through a series of stages to get to the concept of sequence convergence formulated in predicate logic. To begin, we will review the basics of the real number line and see how the properties of the standard ordering on the real numbers are readily formalised in predicate logic. We'll then focus on the notion of distance between real numbers and study a three-place predicate D that holds of numbers A, B and epsilon when the distance between A and B is less than epsilon. With this preparation, we can then get to the formal definition of sequence convergence using what will be a for all there exists for all quantifier pattern. After a bunch of examples and exercises, you will finish off with a discussion of the role of sequence convergence in the digitised representation of real numbers in computers. This brings us to the end of this lesson on mathematics and logic. In the next lesson, we will look more closely at the real number line and its ordering relation, where the order is what makes the number line a line. So see you then.